So let's discuss a little bit more about how valence electrons play a role in bonding in and of itself. And don't forget that the outermost electrons, or valence electrons, are the ones that are involved in chemical bonding. Now this can be a bit complex, but there's a shortened system that's shown in the diagram on the right-hand side here. The number of valence electrons is actually the same as the representative elements group number. So if I go and look at my periodic table, everything in group 1A is going to have one valence electron. Everything in group 2A is going to have two valence electrons. Everything in group 3A will have three valence electrons, 4A, 4, and etc. The only exception is helium, and that has to do with the fact that in the first energy level, there are only a maximum of two valence electrons that something can have. So helium, notice it only has two in its outer shell. Hydrogen and helium play by a little bit of a different rule. We talked a little bit about the octet rule previously, meaning that things want to have 8 valence electrons in their outermost shell, but hydrogen and helium are a little bit different. They only want 2 valence electrons in their outermost shell. So as you notice here, much like many of the things that we've previously discussed on the periodic table, is that the number of valence electrons that are present is a periodic trend. It is based off of the group number that is on the periodic table. And so if we understand and know the group number, we can very easily determine the number of valence electrons that each of these elements has on their own. So just as we discussed before, go ahead and pause the video, and all I want you to do is to write out the number of valence electrons that are present in the following. Take a moment and we will come back and discuss this here in just a moment. So simply put, all I'm asking you to do is to determine the number of valence electrons that are here, and to do that, we just need to figure out what group it's in. So calcium is in the second group on the periodic table. It has 2 valence electrons. Chlorine is in the 7th group. It has 7. Xenon is in the last group, the noble gas group. It has 8. And arsenic is going to have 5 because it is in the 5A group on the periodic table. So pretty straightforward to go through and figure those out. But how does this play a role in how we determine whether things bond or not? Well, let's take a look. So the first thing we're going to do is we're going to start drawing Lewis symbols, and Lewis symbols are just a way to represent valence electrons and how they are either donated or shared when they go through and form chemical bonds. So we're going to take a step back from that. Rather than drawing out compounds and molecules and things like that, I just want us to simply be able to draw the elements and the number of electrons that are present. And this is actually quite easy to do. In order to start this off, we're just going to write out the chemical symbol. And then we're going to add a dot surrounding the chemical symbol for each valence electron that is present. So for example, calcium has 2 valence electrons that are here. We add 1 dot on each side of the symbol before doubling up. So remember, things can have a maximum of 8 valence electrons. So if we start off with 2, we start off at the top and work towards the right. As I look at the ones down at the bottom here, I tend to prefer the symbol that's on the far left, if I'm perfectly honest with you. And the reason for that is it starts at 12 o'clock and kind of works its way clockwise, and then if need be, we double up. So you can actually have 2 electrons with each cardinal point, adding up to a total of 8 valence electrons. So if I were to do xenon, for example, I'd start at the very top and I'd go from 12 o'clock to 3 o'clock to 6 to 9, then back to 12, 3, 6, 9, and thus providing 8 valence electrons that are here. So what I'm going to have you do next is I'm going to have you go through and do that here. I want you to write out the Lewis symbols for the following individual elements. I'm going to do this with you here in just a moment, so stay tuned and I will show you exactly what I'm looking for. Try these out and we'll see you in just a moment. All right, so now that you've gone through and paused the video, we're going to go ahead and write out some Lewis structures for these particular elements. So the first one we're going to do is barium here. If I find barium's location on the periodic table, I find that it has 2 valence electrons, so write out our chemical symbol, Ba, and 1, 2 dots. Just as simple as that, folks. Let's do hydrogen. Again, first group on the periodic table, so give it a dot. Silicon. 4th group on the periodic table, so we're going to give it 4 dots. Chlorine. Group 7 on the periodic table, so let's give it 7 dots. So notice how I went back and I doubled up. Makes it look really nice and neat. And then lastly, neon is going to have 8 dots because it's in that noble gas group. Again, looks really nice and neat. That's all I need you to be able to do for this. So pretty straightforward. Now we're obviously going to do more with it than this, but this is going to get you a really good start in regards to writing out structures, in regards to Lewis structures and things like that. So what we have here is just another example or a variety of examples rather of different Lewis structures of individual elements. So again, notice that the number of dots that are surrounding each individual element is directly correlated to the number of valence electrons that are present in that structure. And again, that is based off of its periodic table location. So you can see all of those there. Pretty straightforward to go through and do. I feel like we're good to move on. So when we talk about the octet rule, this can be a little bit complex, so make sure you stay with me here. Atoms of a certain number of valence electrons are most stable. Remember that we talked about noble gases being the most stable elements of all on the periodic table. Atoms that lack the most stable number of valence electrons will bond with others to obtain that stable number of valence electrons. So atoms are going to do one of two things. They're either going to donate electrons or take them in order to achieve 8 electrons in their outermost shell, or they're going to share electrons in order to do so. Today, what we're primarily going to focus on is the donating and taking of valence electrons. The octet rule is the concept that atoms will donate, take, or share electrons from other atoms in order to get 8 valence electrons in their outermost shell. That is where they are most stable. Some people will use the term happy. Atoms don't really have feelings, so I don't prefer to use that term, but you get the idea. The only exceptions here are hydrogen and helium, which only want 2 in their outermost shell. That plays a little bit more of an important role when we draw Lewis structures for compounds, but still an important rule to know nonetheless. So remember what happens with ionic bonding. It involves the transfer of electrons between 2 or more atoms, and this involves a metal and a nonmetal. So what this means is that when electrons are transferred from one material to another, something is going to lose electron or electrons, and something is going to gain an electron or electrons. Ions is the term that we use to describe atoms with an electrical charge due to a gain or loss of electrons. If an atom gains electrons, gains negative charges, it becomes negatively charged. If an atom loses electrons, it becomes positively charged. So we need to take into consideration that proton to electron ratio, right? We can't change the number of protons. Remember, if we change the number of protons, we change the element that's on the periodic table. But we need to think about the relative number of electrons when compared to that of the number of protons. If something gains a negative charge, remember atoms are naturally neutral. So if something gains a negative charge, it will naturally have more negative charge than positive and therefore carry a negative charge. If an atom loses an electron, there's going to be more positive charge than negative charge, and so therefore it becomes positively charged. So we really need to think about these things in terms of the relative amounts of pluses or minuses that are present in the given compound. That will help us get a better understanding of what happens when these things gain or lose electrons. So if we look at an example here, we're going to look at sodium chloride as an example. Na as a neutral atom has 11 electrons and 11 protons, and chlorine as a neutral atom has 17 protons and 17 electrons. Well, in the process of ionic bonding, and we'll discuss why it only gives 1 electron in just a moment, sodium loses 1 electron while chlorine gains 1 electron. So sodium, by losing that electron, now only has 10 electrons, whereas it has 11 protons. So therefore it has 1 more positive charge than negative charge, and so as a result, sodium will be a positive ion. Chlorine, however, has 17 electrons and 17 protons, but it gains 1 electron. So therefore, it now has 18 electrons when compared to 17 protons and is going to carry a negative charge. What do positive and negative ions do? They attract each other due to Coulomb's law. Remember, opposite charges attract one another. So keeping track of the relative number of protons and electrons is very, very important in regards to ensuring that we understand the difference between when positive ions are formed and when negative ions are formed. As I mentioned before, it is important to remember that ions adjust the number of electrons. We cannot adjust the number of protons to match the charge because that adjusts the identity of the element, and we cannot do that. The charge of the ion is dependent upon the number of electrons lost or gained. So depending upon how many electrons we've lost, we could have a net positive charge of +1 if we've lost just 1 electron, +2 if we've lost 2 electrons, +3 if we've lost 3 electrons, etc. If we've gained electrons, then we have a net negative charge, and that can be -1, 2, 3. Notations for charges are located in the top right of the symbol. So for positive ions, notice that in the top right-hand corner, we carry a 2+ charge, 1+, 3+, regardless of the charge, it is in the top right-hand corner. Many times you see this with the notation that we looked at back in unit number 3, where we looked at the atomic number on the bottom left-hand side and the mass number on the top left-hand side. And the same rule applies to negative ions. We're just going to include negative as a result of their charges. Notice that it's not like an addition where we say plus 2, plus 3. It is 2 plus, 3 plus, 2 minus, 3 minus. The 1 for 1 plus and 1 minus is implied as we go through and do this. But regardless, make sure that you keep track of the relative number of protons and electrons to determine what charge you end up having. So what we're going to do here is we're just going to take a moment. I want you to go through and give the chemical symbol for each of the following ions. Remember, we're thinking about the relative number of protons and electrons as we go through, as we take a look at these individual ions. So take a moment and we'll come back in just a moment to wrap things up here for this particular part of the unit. So as we evaluate this here, it says an ion formed when bromine gains 1 electron. Well, if it gains an electron, it has 1 more negative than positive charge, so it's going to take a negative charge. So Br minus is what we're going to look for here. An ion formed when calcium loses 2 electrons. Remember, a neutral atom has the same number of protons and electrons. So if calcium loses 2 electrons, then we'll have 2 more protons than electrons, and therefore it's going to carry a 2 plus charge. A couple more questions here. Take a moment, and we'll come back and finish up this discussion. So I want to know whether a sodium plus ion has more protons or electrons. Well, notice it does carry a positive charge, so that tells me that it's going to have more protons than electrons. Protons carry a positive charge, electrons carry a negative. A Na plus ion indicates that it has lost an electron, so sodium ion will have 11 protons and 10 electrons. If the chemical symbol X has gained 2 electrons, what would be the correct chemical symbol? Well, if it gains 2 electrons, it's going to carry a 2 minus charge. So it shows 2 more electrons, so we have X with a 2 minus on the top right-hand side. And then a Ga3 plus ion is a gallium ion that has lost 3, gained 3 electrons, or gained 3 protons. Well, remember, we cannot change the number of protons, so that gets rid of the last answer choice here. If it's gained 3 electrons, it's going to carry a 3 minus charge, so it has to lose 3 electrons. You cannot change the number of protons because it changes the element. If we lose 3 electrons, that tells us we have 3 more protons than electrons, so it's going to be a 3 plus charge. Now, the octet rule helps us understand the charge associated with certain atoms on the periodic table. And atoms tend to either gain or lose electrons until they have the same number of electrons as the nearest noble gas. And just like in an airplane where the nearest seat may be behind you, the nearest noble gas may be behind the element that you are looking at. So for example, if I look at sodium on the periodic table, sodium's nearest noble gas, based off of its atomic number, is neon, right? Because neon has 10 protons and sodium has 11 protons. So in order to have the same number of electrons as the nearest noble gas, sodium is going to lose 1 electron, forming a positive charge, meaning that sodium has 11 protons and 10 electrons. Magnesium, much closer to neon than it is to argon, so it's going to lose 2 electrons, and aluminum loses 3. But notice as we move further right on the periodic table, things don't lose electrons, things gain electrons. So for example, chlorine is much closer to argon than it is to neon, so it's going to gain an electron. Sulfur gains 2, and phosphorus gains 3. The typical rule of thumb here is that metals tend to lose electrons while nonmetals tend to gain them. So that's a really good way to figure out if your particular element is going to gain or lose electrons is based off of whether it's a metal or nonmetal. Now there's another way that we can go through and do this, and again, I also want to reiterate here, notice the charges on the individual ions that are present here. Na lost 1 electron, so it's a 1 plus. Mg loses 2 electrons, so it is a 2 plus. And Al loses 3 electrons, so it is a 3 plus. Chlorine gained 1 electron, so it's a 1 minus. Sulfur gains 2, so it's a 2 minus. And phosphorus gains 3, so it is a 3 minus. Well, this all has to do with the number of valence electrons that are present in an atom. And so that can be noticed or represented as a periodic trend as well that we'll take a look at in just a moment. And this slide here just reiterates the concept we just discussed. The magnesium 2 plus ion has the same number of electrons as a neon atom does, but because neon has 10 protons in the nucleus, it is neutral. Whereas Mg2 plus ion also has 10 electrons but has 12 protons, so it carries a 2 plus charge because it carries 2 more protons than electrons. Now again, the shortcut here is looking at the groups and understanding that each group contains the same number of valence electrons. So if we have our periodic table out, we can recognize that elements of similar groups are going to have similar charges because they have the same number of valence electrons, so they're going to lose the same number of valence electrons or gain them in order to make the same charges in the same group. So what that means is that everything in group 1A is going to form a 1 plus charge, 2A, 2 plus charge, 3A, 3 plus charge. And as I move down the periodic table, we're going to skip 4A for now. Most things in 5A form a 3 minus, a 2 minus for 6A, a 1 minus for our halogen group, and 0 for our noble gas group. So this makes it much easier to figure out the charges because it is, again, a periodic trend. It is that concept that Mendeleev put together of this periodic table, and it just so happens that it produces so many unique periodic properties. It really is an amazing thing. So determine the standard charge and write out the element symbol with the charge for the following. So again, it is periodic table based. Take a look at what you've written in the top columns of your periodic table, just like what I asked you to do. Go ahead and write those charges out based off of the group number, and then determine the charges for the following elements based on their periodic table location. Take a moment, we'll come back and discuss. So let's start off with boron. Boron is in that 3A group, forms a 3 plus charge. Nitrogen is in that 5A group, so it forms a 3 minus charge. Calcium is in that 2A group, it forms a 2 plus charge. It is all based on its location and its group on the periodic table. If you can find that information, you get an opportunity to go through. And I guess this is a good opportunity to mention this as well, is that anytime you get an exam, anytime you get a quiz and you get a fresh periodic table, label, label, label. Label your metals and your nonmetals. Label how many valence electrons are present in each group that we've discussed, and label the charges. If you do that, it's going to make your life so much easier as you go through and work through this course, especially when we start going through and doing nomenclature. So ion formation occurs as a paired process. That is, when something loses an electron, something else by definition has to gain it. And as I mentioned before, electrons tend to be lost by metals and gained by nonmetals. So we represent the compounds through Lewis structures, a combination of Lewis symbols that represent the transfer or sharing of electrons in chemical bonding. Now we're going to eventually do this two separate ways. The first way we're going to go through and do this is through ionic bonding. So we're going to be transferring and moving electrons using arrows. The second way we're going to do this is through the sharing of electrons. Now that comes by in a little bit later unit when we start talking about the structure of molecules and things like that. So I want you to consider the formation of NaCl. Sodium forms a 1 plus ion by losing 1 electron, and chlorine forms a 1 minus ion by gaining 1 electron. So what we can do here is show the transfer of 1 electron from Na to Cl. So notice at the very beginning here, when I start off with this particular problem, I write out the Lewis structures for each individual element that's a part of the compound. So I have 1 Na and I have 1 Cl. Then notice what I do is I use an arrow to show the transfer of the electron from the metal to the nonmetal. Again, metals tend to lose electrons, nonmetals tend to gain them. When that 1 electron gets transferred over, Na then becomes a 1 positive charge. We put it in brackets and we put a positive charge on the outside. Chlorine gains that electron. Notice that it now has 8 valence electrons in its outer shell, and it has brackets around it as well and a minus charge. For things like sodium, and I know it doesn't look like it has 8 valence electrons, but the reality is once it loses that electron, it has the same electron configuration as the element before it, which is neon, which is a noble gas, which has 8 valence electrons. So even though it doesn't show it here, anything that shows no electrons outside of it, it's considered to have a full outer shell. All right, and then we have positive and negative charges for our sodium and chlorine. Remember that opposite charges attract due to Coulomb's law. We end up with our chemical compound NaCl. It's a little stormy outside. I'm not sure if you can hear that in the background, but it is thundering like crazy, and I love it. Now, ions may not always match the needs of other atoms. It's going to be dependent upon how many electrons it needs to lose in order to achieve an octet and how many electrons something else needs to gain in order to achieve an octet. So consider sodium and oxygen here. Sodium will lose 1 electron. However, oxygen wants to gain 2 in order to achieve an octet. So notice when sodium donates its 1 electron, that sodium is fine. It's given away its electron and therefore is fully satisfied, takes a positive charge, and has the octet rule satisfied. But notice that when it donates 1 electron, oxygen goes from 6 to 7. It is not stable. So what that means is that we have to have a second sodium atom in the compound donate its electron to that oxygen. So that's where we get a variety of different chemical formulas is based off of the number of electrons that are transferred and the satisfaction of that octet rule. Because each sodium can only donate 1 electron and oxygen wants 2, it requires 2 sodiums in order to satisfy the octet rule on oxygen. So when we see this here, we draw out 2 sodium ions with positive charges. And because oxygen gained 2 electrons, it carries a 2 minus charge instead. So the number of atoms or ions that are going to be present here is going to be dependent upon how many are needed to go through and satisfy the octet rule. So let's take a look at the situation here. Why are 2 chlorine ions needed for every 1 calcium ion? Well, calcium has to donate 2 electrons. Each chlorine only needs to gain 1 electron. So calcium cannot donate both of its electrons to chlorine because that would have 9 electrons in its outer shell and not 8. But if we had 2 chlorine atoms instead of just 1, calcium can donate 1 electron to each of them. So in this instance, we need 2 chlorines and 1 calcium. Calcium donates both electrons, so as a result, it carries a 2 plus charge. Each chlorine gains 1, so therefore it has a minus 1 charge. But notice again, all the octet rules there are satisfied, and we end up with CaCl2 as our chemical formula. So the chemical formula, again, is dependent upon the valence electrons and how we can get all of the octet rules satisfied through the donation and taking of electrons. So what I'd like us to do here, pause the video. I'm going to show the formation of the following ionic compounds using Lewis dot diagrams. So again, draw out the individual elements, think about how many electrons need to be transferred, and then go through and rewrite them in the end with brackets and charges. It can be a bit tricky at first, but once you understand the flow of electrons from metals to nonmetals, this should be relatively easy. I'll show you here in just a moment. Pause the video and we'll go from there. All right, so let's evaluate each of these compounds and figure out what type of dot diagrams we're going to go through and draw. So the first one says Li3N. So we need to draw 3 lithiums. And we're going to draw 1 nitrogen. The next thing we need to do is to put out the number of valence electrons that are present. Each lithium has 1. I'm going to make those a different color. Let's make those blue so they stand out a little bit more. I tried. And the nitrogen has 5. So 1, 2, 3, 4, 5. Okay. Now remember, the whole goal here is for either the metal atoms, or I should say both, for both the metal atoms to lose their electrons and for the non-metal to gain electrons, so that way the octet rules are satisfied. So lithium is going to transfer 1 electron each to nitrogen. That results in our 3 lithiums. Each carrying a positive charge, and our nitrogen having a full octet of electrons now, in brackets with a 3 minus. So again, even if you're not given the chemical formulas for this, you should be able to figure out how many electrons get transferred. Let's do calcium and sulfur here. Calcium, based on its periodic table location, has 2 valence electrons, and sulfur has 6. Calcium is going to transfer both electrons over to the sulfur. And so when we're done, calcium carries a 2 plus charge. Don't forget to include the valence electrons on the nonmetal. Going to carry a 2 minus here, and we're done. So same thing here. Notice we need 2 galliums and 3 oxygens. So a little bit trickier to do this, but again, each gallium 3 valence electrons, and each oxygen has 6. We transfer over the electrons. Remember, to show the correct number of electrons getting transferred to each atom. So oxygen only needs 2 to satisfy its octet rule. So the first 2 here go to this first oxygen. The subsequent 2 go to the next oxygen. And the last 2 go to the last oxygen here. So I'm going to abbreviate this a little bit just because I'm out of space. So again, all it is showing the relative number of electrons, how they get transferred over, and then making sure that you have the correct ratio of ions as well as you go through and figure this out. Now, in some instances, I may not give you the number of atoms that are present. You may have to figure that out. Again, you just need to think, are both octet rules satisfied? If not, do I need to add another positively charged ion? Do I need to add another negatively charged ion? Do I add another metal, non-metal? It's all about making sure that all those electrons get lost by the metal. And then once all the non-metals have gained their electrons, do they have all the octet rules satisfied?